to the microstructural, mechanical, and biological stimuli virtual lab. Professor Sandeep Salami sir, the head of the Department of Materials, Science and Engineering of IIT Kanpur, and Olga Yadavani Singhana, PhD from Florida International University, USA. He has made significant contribution to material science, biomaterials, and nanomechanics, publishing 200 plus research papers and 10,400 plus citations and an index of 39. As a key contributor to the virtual lab initiative of MHRD, Government of India, he developed two ideas virtual labs. First, material response to microstructural, mechanical, thermal, and biological stimuli. And second is electron microscopy for beginners. Today, Professor Alisa will demonstrate how virtual lab enhance experimental learning and bridge the gap between theory and practice in material science. Let's extend a warm welcome to Professor Sandeep Nani sir. Sir, the screen is yours.
that number. And we're exceeding that also by an order of magnitude. In addition, we have conducted around, say, 19,000 such workshops. More than 13 lakh users are trained, and nodal centers are more than 1,500 or 1,600 or so, right? But this data maybe for last 5 years, what you're mentioning, what you're seeing on the small bars of 17 or to 13 lakhs and other numbers. But I'm just highlighting or emphasizing that this is very potential. It has grabbed the attention of multiple users, whether that is student or a faculty alike. And if you see India, you can see there are multiple number of centers, nodal centers, which are spread across the country. From eastern to north to south to west, they all are spread across. And that's where you can see that it is really catching the attention or the traction which actually it required to take it further. And currently we have, even in our own center, we are able to see that we have around 2 millions or 20 lakhs of views which have happened in the last some time for IIT Kanpur as well. And to provide you a background of what virtual lab is, how it is developed, I will highlight that it started or triggered with NPTEL, that's National Program for Technology Enhanced Learning. And then government realized that, oh, we should have or take it a way forward by providing laboratory component also along with the lectures. Because each course was built with 40 lectures, can we also have some labs around it? And the way idea or the objective of virtual lab is to provide a remote access to the labs, mainly for either undergraduate, postgraduate, class 11, 12 students in the discipline of sciences and engineering. So that's how this particular concept of taking virtual lab forward actually was triggered to get a remote access. And the idea is that so can we enthuse students to conduct experiments? Because whenever students are learning in the class, they pretty much actually take notes and they do basically they're left to their own imagination of what they can do with those particular concepts. But how it is being applied, if we can also imbibe that or embed that particular learning, then that learning remains for lifetime. So that will allow one to learn the basic concepts, at the same time apply those concepts through this experimentation. And if these are remote experiments, which mean I can do experiment sitting somewhere, and then again I can access that particular lab happening somewhere else, then nothing like it, right? I will not be limited by the infrastructure what I have. So that was the intent. And also idea was to supplement that with something called as a complete learning management system, which means that I can build tools around it to provide, if so in case in the class, if I have some additional question, I want to have a slow pace, or I want to see some video or some schematics or some animations, I can also add them in this particular system, which is learning management system. So including web resources, video lectures, linking with NPTEL, providing animations, demonstrations, and also as a feedback as well as evaluation tools. So that's how one can learn and go forward. Intent is also to share the costly equipment and resources which are otherwise not available to many because of either economic or because of geographical or because of time constraints. So that way it becomes very limited in terms of usage, but can those be shared? If I have equipment at one place, it may not be being utilized for 24/7. Can I utilize it through virtual labs? So that is the idea that we can extend the usage of any particular equipment. Now, the way virtual labs were developed, so what is actually a virtual lab? So the idea is that to provide a glimpse of what is happening, what can be done hands-on through the tools of IT or information technology. I imbibe animations. I allow the student to perform some experiment and have the same learning as I might see from a actual experiment. So I'm putting this aspect of laboratory on a virtual platform. The limitation of virtual lab, definitely you can maybe imagine that it is being done on a ideal case. In reality, I may see some frictional forces. Say in case I'm using a experiment of a pendulum and I want to measure what is the acceleration due to gravity. In reality, I will have some resistance because of air. But in simulation, I may need to ignore that because it is an ideal condition. So that way, there may be some nuances or some fine tuning that may be required for a virtual lab, which is being accounted maybe now these days. But now take it forward. The idea of virtual lab is to allow a student to learn at their own pace. So it's a web-enabled system for remote learning and experimentation at one's own pace. Say I may be a slow learner for say experiment number one. Experiment number two, I may be well conversant with that. I may do that at a faster pace. But in reality, many times experiments are duration of 3 hours. So I'll be required to learn everything in 3 hours, though I may require say 5 hours for that particular experiment. For second experiment, I can do everything in say 2 hours, but I am forced to stay for 3 hours, right? So that way I'm either not allowed to spend more time or I am wasting my 1 hour extra in some other case. So can I tailor that particular experiment so I can learn at my own pace? Second part is learning at own place. So it also depends on how can I utilize being in a certain place and then still learn. Say I may be traveling on a bus, or I may be sipping a cup of coffee in cafeteria, or I may be traveling and then I want to conduct an experiment. That may not be that feasible experimentally. So can I learn everything at my own place of comfort? So by sitting on a couch, I can maybe open up my cell phone and learn at my own place of comfort and get some understanding of these particular labs. Other than that is also time. So I can access at any time. Typically, labs are placed either morning 9 to 12 or in the afternoon 2 to 5 p.m. Right? But if I am very active say early in the morning, say at 4 a.m. or 5 a.m. and I'm interested in conducting a lab, people will not open up lab just for me. Or if I'm very active later in the night, maybe say 10 till 1 a.m. in the night, again the lab will not open only for me, right? So that way, if I want to conduct at any given time, I have to just open my cell phone and then do the experiment or conduct the experiment. And that is, I think, that's what makes the virtual lab very fascinating and attractive, that I can do a experiment at my own pace, own place, and at any given time, right? And the idea of those particular labs should be to provide learning basics or advanced concepts. And also there is a virtual lab available at all levels, whether it's a class 10th, 11th, 12th, or undergraduate, postgraduate. And these are also ideas to take forward for research. It doesn't end with only pedagogy, it means only undergraduate or postgraduate teaching. It also can provide you some ideas of how to pursue research. And that is the intent, that to challenge, to establish virtual labs in major areas with a variety of resources for enhanced learning. So everyone is encouraged to utilize these labs and take it forward. Nowadays, virtual reality also is coming into picture. But the way the conceptualization of virtualization started was in variety of means. So there were multiple steps through its saw a transition. So when things started, the idea was, can we remote trigger? In the sense that if you are sitting in Kannauj, you can send a sample to IIT Kanpur, then I can provide you access to that particular equipment and you can control that equipment. So by sitting in Kannauj, you can conduct an experiment, which is called as a remote triggered experiment and control. So you've taken a control, you're running a particular test, say a tensile test. So you've sent me the sample already, which I fix it, and then you can do the test. But now, so that is one way to virtualize, right? But then that has some problem or some issue. Say imagine the connectivity fails. So you gave some command of grip to go closer, and somehow the connectivity failed. And that command can, allow this particular grips to come and then crash, right? So at no fault of yours, machine has gone down because of the crash, because of poor internet connectivity, right? That can happen. Another problem is only one person can operate, right? If you're operating, if there is another person sitting in say Delhi or Bombay or somewhere else, if they want to control the same experiment, they cannot. Only one person can conduct the experiment at a given time. So that is also a limitation on number of users. One more disadvantage is, though you're conducting tests sitting at Kannauj, I need a person at Kanpur which can place the sample and allow you the access, right? So I cannot really operate it 24/7. I require a operator to be there whenever the experiment is going on. So that way it also limits the usage of the equipment not to 24/7, but to only limited duration when the test is being conducted. So it required new measures of taking it forward for better utilization. So then second term, which second way of virtualization which came by was measurement based. So in this case, what I'll do, I will conduct the test, say tensile test. I'll take variety of samples or variety of parameters. variety of materials, parameters, and then whatever I want to conduct. But then what I'll do, I'll measure each and everything. It means that I'll provide the composition of sample one, which can be say steel sample. Second one can be titanium sample. Then I can do the tensile test at given extension rate. So I'll have load displacement curve for sample 1, sample 2, sample 3. I can also change the geometry of the sample, geometry 1, geometry 2, geometry 3. I'll note down all the values. I'll show how the curve looks like. I'll show the sample and I put it for student to learn from in the measurement based experiment. So in this case, I have taken the measurements and I'm just providing the value for the student to learn from. The limitation here becomes that I only have those much result available. I cannot vary. If I want a different sample diameter, I cannot. If I want to have a different set of sample composition, I cannot. Right? So sample geometry is fixed. Type of extension that I'm giving in the instrument is fixed. Right? So those things are the limiting factors. But nonetheless, that was measurement based. Now there is another part which came by to enhance the quality of learning was video recording or playback. So in this case, entire process of the experiment is also getting recorded. Even when the sample, how the sample is being loaded on the instrument, the real time result that you're getting from the instrument, everything is getting recorded and you can play it back. So it may seem very similar to that of the second, which is measurement based experiment. But here there are some secondary information that is very, that helps you learn to a larger extent. Like if I am holding a sample and putting it on the sample chuck, subconsciously you will see that what is the sample dimension with respect to what your hand is, right? So you'll put how the sample is being put in. So that way you will get some extra information. Then once you see the sample is getting extended, then what is the load displacement curve you're getting from in the machine, and then how that load displacement is getting converted to stress strain, right? So all those things and how carefully I have to place the sample. What about the sample alignment? What is the type of chuck or the load cell that is being placed on the instrument? So those secondary information you can always get a feel of by the video recording or playback system. So that adds additional value to the learning via this virtualization. Now the last one which came by was simulation. And now here we add animations to provide teaching basic concepts. And initially it started with utilization of licensed software. It means like MATLAB or ANSYS or everything like that, right? But that a limitation because it's licensed and everyone may not have that license available to them. So then it started with simulation utilizing some licensed software, but now it is triggering towards having utilized the open source. So now things are available on open source and one can simulate. The advantage of simulation is now I can provide any variable, right? I am not limited by the sample geometry. So if I have an instrument where I want to do tensile test, I can give a sample as long as 1 meter or 1 millimeter or 1 micrometer or 1 nanometer, right? So I can provide any level of variability. Even when I'm doing a test for pendulum to see acceleration due to gravity, I can give the string length to be order of 1 kilometer or the weight of the ball, which can be 1 ton, which is practically not that easy, right? So that way I can start varying those variables. And added advantage for simulation is I can give any extremes of combination of parameters, still the machine will not break, right? I can provide so many things, but machine will not break because there is no machine. It is all simulation. Whereas in measurement based, video recording based, remote triggered based, I'm using actual equipment to provide me the output. In simulation based, there is nothing like this, right? So that's how I can virtualize the system. By remote triggered, first initial phase, then it became measurement based, then it became video recording based or playback based, and then simulation. And the idea is to be able to learn the concept through virtualization, right? So that is the overall intent to be able to grasp what mechanism is happening, how experiment is being conducted, and what you take out of it. And one very important part, because I think most of us are here as teachers, so we should be able to distinguish between what is data. So experiment is not data collection. Typically, we have a set parameters. Oh, take the sample of this dimension, utilize this particular property at other dimension or other parameter. and just write down the values or do the titration, and you get something, get some numbers, and that's how you will get it, right? But idea is not that. No, data is not equal to learning. Data is just those numbers which will help us create some information. So gathering of certain parts actually is data, but how do you connect those parts start to form or provide information? So when I am just getting or researching or absorbing, that's data. But when I do something, I can now vary the parameters. So in case if I'm doing a tensile test, if I just report for this particular sample, I got this much of a yield strength of fracture strain. That is nothing but data. But now if I see, if I vary the sample, then if I get the stress strain for sample one, which is say steel, versus second sample say which is aluminium, how can I connect the ductility with respect to strength or the deformation with respect to fracture strain? So that way I can start connecting, and that data now starts converting to or becomes information that I have higher ductility for aluminum compared to that of steel, right? So that is nothing but connection of parts. Now, once I start to see how can I utilize the information to get even broader picture. Say if I take this particular steel sample and if I'm testing them at room temperature, and if I want to see what may happen at high temperature or very low temperature, right? So how things start to interact with one another. So how load will get affected by temperature, one part, right? What about microstructure itself? In steel itself, if I change the composition or if I have distribution of second phase particle, how that might start to affect the yield strength of the material, right? So now what I'm doing, I'm letting the variables interact themselves. How the load displacements are getting affected by temperature, by the same composition but difference in the way the phases are getting distributed. Now the variables are interacting with one another. And that's how I start to get a broader picture. And that's where the information becomes more or less like a knowledge, right? So from data, we have gone to information, connection of the parts, then going with interaction, which is nothing but knowledge. And the last step, as you can see, that is being able to reflect. And that provides us wisdom. So now from actually doing the experiment, we are coming to wisdom where we can reflect and we can design the experiment. Right? So that's how this particular transition is. The learning pyramid from data to information to knowledge to be able to join and reflect. And that will help us to create something new. Right? So in terms of providing a novelty, being able to join different wholes, which mean WHOLE, for various systems, and then I can create something new as such. And how to go about using the virtual lab? So there are multiple facets to it. So start typically with a pre-test. So whenever we start experiment, we go with a pre-test, that is providing a self-analysis. It will let you know where do you stand. Then second step is to get to the aims and specific objectives. So aim is typically given, you get into it, then go for pre-test, then see what are the objectives. So what this particular experiment is trying to teach you. Once that is known, then go through the introduction, theory, methodology. So theory is very, very important. What is it that forms that particular experiment? Then methodology will let you know what are the steps required to conduct that particular experiment. And there may be some NPTEL lectures which are coupled with those particular methodology of theory. And now you also have simulations. So methodology will also talk about simulations that are being part of that particular experiment. So once you've gone through self-analysis, aim, objective, introduction, theory, methodology, then get on to seeing simulations. So once you go for simulation or experimentation, that will actually allow you to try vary the parameters and then take it forward. And there may be some videos available which will let you understand what this experiment is all about. And you can also replay if required. NPTEL lectures or videos. Now, once you've conducted the simulation, it may ask you to note down certain results, values, and may ask you to plot and find certain, say, activation energy or certain value of resistance or for that particular circuit. So that way you can go about learning it. And once you come to results analysis, spend time on it. Why this is the way it is. And then once you have gone through that, that will start to give you some indication of what this conclusion of this experiment is. What are the findings and what actually it means. And then you take post test for self analysis. So when you took pre-test, it was maybe at a basic cursory level. Post-test maybe a little more rigorous in some sense, that in terms of our understanding, and then see where do you stand, and then whether it requires any further learning on that. And going forward, it will definitely help to enthuse the student to learn and apply concepts, and also to encourage the student to pursue higher studies and get into research. And also postgraduate students can also find this virtual lab very interesting, and also can get some ideas for research topics, which I already highlighted. And again, idea is not to duplicate the equipment which is already available, and then one can utilize and do parallel processing for that. And in addition, once we get into simulation, that simulation can also be very helpful for a student to pursue higher studies, like in masters or PhD. And those tools are available, but idea is we make them open source. So instead of can we avoid the licensed software and then develop simulation tools from, which from open source codes. And so that is the intent, that to create or produce this handy simulation tools on open platforms for additional learning for the system. This is family of virtual labs. So there are multiple IITs, NIITs, triple IITs which are involved, and which actually formulate this national consortium of virtual labs. And you can search the experiments via, going on the platform. You can see it either in terms of domain or in terms of which IIT or which triple IIT or which NIT is actually has made those particular experiments. So you can spend some time out there. Hmm? So I will not, take you back to this, but I'll just take you through one example and then maybe take it forward of what can be done. So you can see there's one lab, material response to microstructural, mechanical, thermal, and biological stimuli from IIT Kanpur on the top right part. And there are multiple others from various other IITs and all. So we take it forward. So can someone maybe try to read this? It looks very confusing, right? So it is not easily available to grasp. So maybe you can just check what you can make out of this particular broken letters which are probably out there, right? So let me throw light on it. Now I think it becomes very easy to read, right? So typically, sometimes our mind is, with so much clutter that we sometimes forget to take a break, and maybe some visualization, some trigger helps us get back, because mind is really very sharp. The brain is amazing. Can we give it some, food for thought? And that's where the virtual labs comes to rescue, that we can provide some additional information, whether it is corollary to, say lectures, providing lectures, animations, or some additional insights. So the hidden information is still the same, but because of additional, supplements, you can always see that it benefits you in some sense. So just to take you forward, modern age definitely brings new forms, new challenges for educational progress. Conventionally, I think when we were taught, probably we did not have, internet, or maybe these tools available, laptop that easily, phones that easily. Now, each and every student has a cell phone. Can we utilize that to impart some education, right? So in engineering education, we need to worry about theoretical knowledge as well as lab work. Why lab work? Because lab work will allow us to apply that particular information and also build up advanced concepts. And if you can engage the student in teaching plus lab, then they can retain that information. And what else if they can do the experiment at their own place, own pace, and own time? So they can conduct whenever they want, wherever they want. So that way, remote labs are very, very good solution for performing lab work. So if I am a student, if I have the opportunity to see something on my mobile phone, instead of spending time maybe on Snapchat or maybe on WhatsApp, I may get engaged or may get attracted to conduct, experiments on virtual lab if it is available. So that is the intent, that we can encourage and direct the students to utilize their time for better learning. Being said that, I will still highlight or mention that no virtual lab can replace real hands-on. So this is a factor which again I'll emphasize on. No virtual lab can actually replace real hands-on. But actually, I have been giving this lecture on utility of virtual labs for last maybe 20, 30 minutes. So why I was doing that? So if virtual labs cannot replace hands-on, then why should we at all go for virtual lab? Okay. So there are multiple reasons for it. First thing is, yes, in case if some place we don't have equipment at all, then at least I will have some information available through virtual lab. So instead of having nothing to having something via virtual lab. Now, and not more important part also is, out of say if I have a particular core subject which is a mechanical engineering or say material science, how many students will actually get into core jobs? So 10%, 25%, right? But when it comes to experiment, we are bound to ask all the 100 students to come and do the experiment of metallurgical or mechanical engineering, right? Which is not required. And even if they're sitting there, they may, I mean, do something which is probably not mindful, in the sense they may not be paying full attention, and then they will basically disrupt the others. So, or it may even damage the equipment. So if I am doing virtual lab, then at least I am not putting the equipment to danger in that sense. Right? So that is another part. But in addition, if there is a repository of around 10, 15, 20 students who are actually interested, and by pursuing virtual lab, they will have a very good feel. Even if you have actual equipment, now these students, if they get on to doing virtual lab, now they'll be more confident in handling the real life experiment. So even if you have an equipment available, still you should encourage students to go through virtual lab, learn about that equipment, and then actually get onto the actual equipment, because that will have now lower chances of getting the equipment damaged. But more importantly, now they will be getting to seeing utility, or also they would have gone to theory experiment, so they will know what to expect out of it. So instead, when they start the experiment, they are not doing the experiment; they are actually designing an experiment. So that way, they will be very, very helpful, right? So I'll take a maybe a minute or so break, but I will highlight one or two points here. So labs are again, let me again highlight. So labs are very, very important. And if you allow a student to conduct an experiment, on actual instrument, there is a typically group of 3 or 4 people who conduct an experiment. And out of those 3 or 4, maybe one is very interested, and they will make the connections or put the samples in. And one may be taking the readings of how things are happening. Another two may not do anything. They'll just probably make fun, keep doing, keep making fun of the other two, or will not pay much attention. So in the process, only one probably has learned. One has taken the reading, other two probably are just there physically, not mentally. And whenever a student goes to conduct an experiment, they are very cautious not to damage the equipment. Because if something goes bad, they'll be held responsible, right? So that's a typical intent. So they'll be just worried about mechanically how to do this, get the right reading, and then leave the lab. They have no intention of maybe learning as much, but they are associating it to an activity. They'll retain the information, but in the process, the intent was not to learn much. But if they go through virtual lab, if they've gone through virtual lab, then they will have a better idea of what is the capability of the equipment, what is the theory behind this particular working, functioning, what are the correlations. So in the mind, they are already very excited of what nuances, what subtleties, what new insights they can get out of this particular experiment. So now they are actually designing the experiment, right? So it is not merely just doing the experiment mechanically, but they have now designed and now they're conducting an experiment. So that way it becomes very fascinating for them to be able to see the correlations, interrelations of that particular parameters, experimental parameters, and they are more keen to see what may come out at this particular comparison of either material parameter or mechanism parameter or any other external parameter, right? That was the intent of virtual labs. I'll take a minute or two break, or in case someone wants to have any question, they can quickly ask. Then I'll go to the specific lab of material response to microstructural, mechanical, thermal, and biological stimuli. Has anyone any quick question for me? If not, then I may then get going, right? Any quick question? No? Then I'll let me get going, huh?
Sir, I have one question.
Yeah, please go ahead.
Actually, this is a very interesting topic. I am Professor Manoj Shukla, director of this institute.
Dr. Manoj.
I am very much interested in all these works. अच्छे लगते हैं because many times virtual labs are also quite important. At least in Corona time, it was quite useful. So sometimes a person who want to know something better, they can experience it at their hostels also, at their home also. They can revise the things because every time it is not possible to for them to visit the lab.
Correct.
The question is that how do you feel the what is the future real future of this particular scenario in our country?
Okay, sure. So not in our country, I mean also abroad, this is getting very popular. So we have to start complementing it with what the technology is. So now currently we're heading towards AI, ML, virtual reality. So experiments are, I mean, to provide hands-on experience, and now hands-on experience is available by putting something in your near your head, and then you can actually experience that.
Yes,
So it is also going towards virtual reality, imbibing tools which are like machine learning tools. So if I've done the experiment 100 times, can I embed the data in that AI tool and then experience it via virtual reality? That's where the I think direction is heading towards, at least in that direction.
that's great. That's great. Thank you.
Thanks, thanks. So now what I'll do, I'll take you to one of the experiments, which is actually generation two, which so earlier was remote triggered, generation one. Generation two was something on the measurement based. Then generation three was video lecture based. Generation four is simulation based. And generation five, which is coming up, is on the virtual reality. So I'm talking about much earlier, generation two. But I think that will give you a feel of how things have changed. So I'll take you to generation two and maybe then generation three or so. Then I think you'll get a good feel of what has happened.
Thank you.
Thanks. So now this is the lab which was yeah quite some time back, maybe 10, 15 years back, and then it had contained 10 experiments. And idea was to see what the materials are doing, how the material will respond when you have a different microstructure or mechanical property or thermal or biological stimuli which is given to the material, how things will actually happen. And the genesis behind this was, say, if I have two chairs in front of me, one may fail early, right? Other one may maybe little stay a little longer. That is because the way microstructure is governing the performance of that particular material, and that way one will fail much earlier than the second one. And similarly, so in there we also have multiple properties, like we have high temperature performance via creep. I can get the hardness, modulus, indentation of via using nano indentation. I can talk about the materials response to biological environment, which is how water will attach, how protein may attach, how cells may attach to a surface. I can see that via wetting and fluorescence microscopy, and also about energy materials like solid oxide fuel cell, which is via ionic conductor. So we had put them into multiple baskets, and maybe around 10 experiments were essentially made. So in summary, it was creep, which is thermal plus load effect, indentation, which is mechanical response, fluorescence is again biological response, wetting and fluorescence, I'll put them together. Wetting is surface, and then you have biological response, and then conductivity is via for energy materials, right? What I'll do, I'll take you one by one. So this is how the lab looks like. So once you get a chance, you may take a look at it, go through it. So this is how the virtual lab actually looks like in terms of its feel. And these are the 10 experiments. So I'll urge you to go through the link. I'll share the slides if required. You can see on the top. It is called as material response to MRMSMTBS, right? So it is material response to microstructural stimuli, microstructural, mechanical, thermal, and biological stimuli. That's how this is acronym. But anyhow, so these are the 3 experiments for creep, indentation, wetting, fluorescence, and ionic conductivity. So these 10 experiments are actually made. I will not go in the detail, but I will just highlight or summarize what actually each concept mean. So first one is on creep. Creep. So maybe if you don't know, or maybe some of you may know about creep, it is high temperature plastic deformation of a material. Again, high temperature plastic deformation of a material is called as a creep. property of that particular material. So what I mean by high temperature, high temperature may mean very different for everyone. So typically before the winter starts, I start to feel very cold. So my tolerance for cold is very bad. Same thing with materials. So if I take tungsten, which is used in the filament of the bulb, even 1000 degrees centigrade is not very high temperature. And for materials like lead, tin, or solder alloy, even room temperature is very high temperature for it, right? So it is a material dependent property. What is the melting temperature of that material? With respect to that, I'll have to say whether it is high or low temperature, right? So if I had to expose a material to high temperature, say you talk about turbine blades. Now, when you're riding in an aircraft, the idea is to get the maximum utilization of the fuel. I would like to operate the material at the highest temperature. And what will happen at high temperature? Material will start to deform. It cannot take its own load, right? If you start to heat something, you'll see that it starts to sag, will deform. And that's what we want to avoid, because if you imagine a turbine blade operating at very high temperature, it starts to deform. Then it itself will collide with the casing, and entire aircraft will come to flames. It will basically burn out, right? So we want to retain the structural integrity. So that's how you define the creep in multiple stages: stage 1, 2, 3. So one is called as a primary or transient creep. Second is steady state. Third is the tertiary creep. But we also see that there is something like instantaneous deformation, that is stage 0. So if I apply a certain load to the material, it deforms. And that deformation can be instantaneous. That is actually instantaneous. That is called as epsilon 0, instantaneous. Then with time, you can see the x-axis is time. And with time, material will start to experience some sort of a strain. It will start to deform slowly. That is stage 1. In stage 2, it is more or less like a straight line. And that is what governs the experimental or engineering prediction of the lifetime of that particular component. So for a given temperature, I need to get this curve of creep strain with respect to time. If I have a higher temperature or a higher load, the curve may start from a higher instantaneous deformation, and at lower time itself it might fail, right? If I increase the temperature or if I increase the load at which the deformation actually happens. And in the stage 2, you can see there is a balance between dislocation climb or blocking by obstacles with respect to the strain hardening. So material is hardening, at the same time there is a sort of a recovery in the system, and hardening at the same time there's a deformation. So they actually so strain hardening and recovery start to balance one another. Recovery means how easily the dislocations are flowing and how easily the material gets hardened because of the deformation via dislocations. But anyhow, so that is what is governing the lifetime of the material. So stage 2 is very critical, and we have incorporated exactly that. So how can I prolong this region? So I can prolong this region by making the material stronger. And how do I make the material stronger? So it is more like this. If I take a carpet, and if I want to move the carpet, what I'll do, I'll create a kink, and I'll push that kink towards the end. So in essence, what I have done, I have moved the carpet little further. So I can also take the carpet, I can lift the carpet and push it, or I can roll the carpet and then again take it further. But in that process, I'll have to spend extra energy because I'm taking care of the entire carpet at that particular given period of time. I've rolled it, complete carpet, and then I am putting the energy. So, but here you can minimize the energy by just creating that extra kink and then pushing it forward with your leg itself. But what I want to highlight here is, if I create some stoppages, if I create the kink and put my leg on it, I don't let it move, then I have stopped the deformation process. Same thing I can do in materials. I can put some ceramics, I can put some dispersoids, which will not let the material deform. I can utilize a high temperature material, and that's where I can improve its high temperature property. And those aspects are basically given out there. If I have what is the size of that particular impediment, what is the density of that impediment, so those are restricting the movement of that dislocation, and that's how I can prolong and I can design the material. There's also NPTEL lecture available to that. There is also a video available with respect to that, so that also you can take a look. Another feature is called as nano indentation. So it is indentation, which means probing a surface at nanometer length scale. And just to let you appreciate how small is nano, so our hairs are orders of say 100 micrometer thick, 100 micrometer. I'm talking about 1,000 times smaller than the thickness of hair. That is around 100 of nanometer, right? Why is that important? Because in any material, I will have multiple grains, which are called as a, which are of maybe say similar or different material. That is one part. So in case I want to see how multiple phases are there in a system, I can probe each and every one, each and every grain via this technique. Otherwise, conventionally, I get an average property. So if I have a sample, I have one material, I'll do tensile test or indentation test. That will give me one value. But here I'll get value for each point. So now I know exactly what is the contribution of each point in that particular material. I want better property, then I can take out one and I can substitute that with some other which is better in terms of performance, right? So that will give me a better refinement of the property for that particular material. And that is what this particular technique helps us. Other way also, you can see that if I want to measure the property of say electronic circuits in my mobile phone. So circuits also are very complex. Some connections are as fine as micrometers. Some layers are as thin as nanometers, right? Nanoindentation can also probe the properties of those. So I can exactly know what is the level of damage or stresses being incurred by them. And I can measure hardness, elastic modulus, plasticity or elasticity part of it. So those also are very, very important. So here what I'm doing, I am loading the sample. So it goes like this. So once the load and displacement, it starts to load up. I hold it up for some time to ensure that it is getting equilibrated. Then I unload. When I unload, during unloading, I get to see what is the elastic response of the material immediately. So I can see what is the level of elastic recovery during unloading. I can get to see what is the stiffness of the material. I can also see what is the plastic component, what is the elastic component. So that way I can get to see the elasticity or plasticity of the material. At the same time, if I see displacement, what is the maximum depth to what is the residual depth or final depth or contact depth, that can allow me to measure the hardness of material as well. So through this, I can also get to see the mechanical properties of the material. And also there is associated NPTEL lecture, which is itself 1 hour. So you can maybe see the nuances or the refinements of this process of nano indentation by going through this particular lecture. So if you want, I can maybe really, so for typically what I do, I take around 45-minute lecture for each of these concepts, whether it is creep or indentation or wettability or even the biological material. So I can maybe talk about a lot about each one, but I'll urge you to go through this particular link, which maybe I'll share the slides and then you can take it forward through that. But the main thing to highlight here is sometimes when the material is scarce, if I only have limited material, or if I have the electronic circuit, which are again very, very fine, very refined, order of micrometers, right? Or when I have multi-layers, especially in the current, electronic systems. So can I measure the property of each one? And then I build up the whole. And that is all possible via nano integration. So that is developed quite some time back. Another one is wetting or wettability. So I see that if I have some surface and I put water droplet on it, if the contact angle is less than 90, I call it hydrophilic. And if it measures contact angle of more than 90, I call it hydrophobic. And if I get to see contact angles more than 150 degree, we call it super hydrophobic. So typically you will see lotus leaf will have a super hydrophobic response, right? So water will not really stick to it at all. It will form a bead and it will basically roll off. And these structures are very, very important because if I want to design something for the body, say I want the bones to grow. In that case, I may want the surface to be hydrophilic. So once the surrounding fluid comes by, then it will allow the protein to attach. Then that protein attachment will lead to cellular attachment. In that case, I want something to be hydrophilic. But when I talk about cardiac systems, like stents or anything else, I don't want the blood to clot there. Because if blood clots, it will stop the flow of blood and it will get to cardiac arrest. So in that case, I may want to make something super hydrophobic. So to the stent, I will coat something which will not lead to any clot formation of the blood. And I would like the system to have very high levels of hydrophobicity. And there are multiple other examples. I may not get into that right now. But again, there is a 1 hour of NPTEL lecture which is built up available on YouTube itself. Right. Also, the link to the experiment is also listed here, contact angle measurement. So this also you can probably take a look. Right. So it is nothing but the play of solid, surface energy of the solid, and surface tension or surface energy of the liquid. How do they play a part? If solid has very high polar forces, high polarity, system of liquid, which is water, will typically be hydrophilic. Polarity will attract each other. If I have non-polarity or dispersive component, which is very high, in that case, like some organic material like polytetrafluoroethylene, right? In that case, I may not like the water to stick on it. It will be super hydrophobic. So that way we can play with the surface, and that will alter the consequent response of the protein and then cell. And how do you observe cell? We can see through fluorescence microscopy. So in this case, we add a dye, some sort of a coloring agent in the cell. So that cell takes up that particular coloring agent. And then laser starts to illuminate, starts to excite that fluorophore molecule, which is nothing but chemical which takes up that energy of laser, gets excited to higher energy state. And when it relaxes, it releases a color. So I can now put a dye, like in this case, if I put a Hughes dye, it will be taken up by nuclei. Once I excite it with laser, once it is getting relaxed, it will give a blue color. And similarly, if I take a Alexa floor, cytoskeleton of the cell will take it up and it will appear green. And similarly, if I take mitotracker, the mitotracker will take up this particular dye when I excite, and then it can give me red color. So now I have one image which is showing blue color of nuclei, another image of green containing cytoskeleton, and third image containing mitochondria, which is red. Now I can integrate all the three together. So now I can see a colorful picture of blue, green, and red. Wherever blue, nuclei, surrounding by green, which is cytoskeleton, and within that cytoskeleton, I may see a red, which is mitochondria, right? So I can get a combination of all these colors in one image. It requires image processing, but I can now get that via fluorescence microscopy. Other one is ionic conductivity. It was actually an experiment in itself. So it is specifically for solid oxide fuel cell. How can we utilize any gases which are any fuel which is say methane or hydrogen, and at the same time get higher efficiency. Typically mechanical system suffer from this Carnot cycle, and they will lose out energy, typically efficiencies order of 40%. Here efficiency can be as high as around 80-85% with some recirculation of this particular energy. So that way we can utilize this system, having air on one side, fuel on other side, and then letting the oxide ion pass through an electrolyte, and then recombination will lead to this conversion of energy, chemical energy to electricity directly. So there's another part to it, right? So that's how these particular 10 experiments were completed, and you can get much more insights about them in the link. Also, there are other experiments, so which are maybe next stage of experiment. Let me see if I can take you through that. Just give me a second. I think so that way it will also give a feel of how things are becoming little different than. Then I'll come to the conclusion, but let me just take you through the virtual lab microscopy. So this is a newer set. So here what you can observe that it has a very standard format. So you can play a video. So video is order of say 15 minutes. You can play that video. It will talk to you about what is electron microscopy. And then so first you can see the aim. What is the aim of the system to learn the basics of electron microscopy, and what is the intent? Student will be able to learn X, Y, Z. Then you come to theory, and in theory you will see the matter. And you can see how detailed it is. It is a schematic. It talks about electron beam, how system will interact. Then what about the instrumentation, how it is made, various levels of electromagnetic lenses that are available, Then also about importance of vacuum, filament. So you can see it is pretty detailed in that sense, right? And also about what is the depth of field, depth of focus, and everything else. And also there are some other resources available, NPTEL lectures as well as SCM lab. There's a pre-test, so you can go through that, see what is you basically know about it beforehand, then about the procedure, what you need to do in the simulation, and then in the simulation itself. So what is so this is a power button, you click on it. So I take a metal, I basically put it and drag it out here. Sample holder is little here, so I'll take this sample, place the material here. So then I put the vacuum level, I set the vacuum level, I put it low vacuum, set it. So it is mentioning that, oh, it is not correct because vacuum should be in high vacuum state. So I put it HV and then set it. Then it is creating vacuum and so on, right? So I'm just telling that there are also simulations available which will let you see, that will ask you to put the accelerating voltage, beam on, set. Then if I put the magnification as okay, it is showing it here, maybe display. And if you want to go to higher magnification, you go to higher magnification, 500, set. You see the system is now changing, right? So microstructure has now become very different. At 2.5 kx, set, what has happened? Image has become different, right? So that's how you can start to play with this particular module. You can also play with the brightness, contrast. So brightness, contrast can also be altered. It will all appear in one single page, I think, because my laptop does not have that setting. It is not showing it rightly, and it can also play the contrast. You can play with contrast, right? And you can also save the image, right? So that way it is pretty nice and neat in that sense, right? So I'll urge you again, request you to go through various experiments, and I'll be happy to share these slides with you. And there are also like basics of physics or introduction to Python programming lab. There are multiple such experiments available. Should utilize these websites, and also to create new experiments. It's not only that I have to use it. That is not the intent. Definitely, we have to use it. Talk to your colleagues that these things are available, use it, and then come up with developing your own experiment. That is the intent, right? So talk to your colleagues about this availability, learn experiments from other disciplines, expose and encourage students to learn from this particular material, also provide your feedback. But now in the end, we would like you to participate, partner, and create something what is specific to your course. And that is the intent, that please come forward. And what it requires is a group of a faculty member, maybe one student from IT background, and three or four more from the technical background in the domain what you want to develop the experiment on. And then see how it suits your own pedagogy, the way you teach students. Can it provide you a visual, a treat for students to get engaged and then get something more from that particular concept? And that is the intent. Hmm? So with this, I think more or less I'll stop now. I thank Ministry of Education, which has supported this particular virtual lab portal. A team from IT Delhi, Professor Ranjan, and also Dr. Ravish, Mr. Rajiv at REC Kannauj for inviting me here. One thought I will leave you with, that there are plenty of obstacles, typically in everyone's path. I think there is overload of responsibility to teachers. Students also, they have their own, I think, way of dealing with teachers. But at the same time, though there are multiple limitations, don't let yourself become one of the obstacles. And unless teachers succeed, India will not succeed. So I think a lot of onus is on us to make sure that we take it to the next level. Hmm? With this, I'll stop here. I'll be happy to take up any questions, and I think it can also go as a discussion. Thank you, everyone, for your patient listening. Yes, I think I can see there are some links provided in the chat box. I'll urge you to go through them: electron microscopy lab or even microstructure, material response lab. It will, I think, be very helpful in taking it forward. And these are, one is simulation based, other one is like measurement based, and now these are being added up or padded up with multiple videos, also animation. So that's how I think it will help the visualization and learning, right?
Thank you, sir.
Thank you.
Thank you, sir. Just I invite to Director Sir, Professor Manoj Kumar Shukla, sir, for the vote of thanks.
Thank you, sir. It was a really nice experience for me also. I'm a little bit unknown to such area, not very much familiar with that. But what I feel that the augmented reality and virtual reality, they are both the immersive technologies that blend digital content with the real world. That is AR, or create an entirely virtual environment for the students as well as the faculty members. It is quite promising area where a lot of work has to be done still, and a lot of work also has been done till now. So I feel that I hope that our students, our faculty members, will work further in this area with your little guidance, whatever is available from your side. I would like to request you also to guide our students as teachers if they are working in this area. I really thank you for this your kind words, kind session which you have conducted for our participants. Thank you very much, sir. Thank you.
Thank you, Shukla ji. Maybe Dhananjay, Mr. Dhananjay also is here. Maybe I'll request him to maybe generate a poll and see who all are interested. So maybe
Certainly.
we can right now we create a poll if required through this and see how many are actually interested in participating. Why I'm highlighting that is I think it will be a good start that we have a faculty member and few students, and they can come up with also contributing to virtual experiments. And we also are keen on conducting either e-bootathons or workshops which will
Sure.
allow one to start from scratch. So from scratch, they can come forward and develop at least one experiment. It may take a month, but I think
So
it will be very, very beneficial.
I would like to just suggest
Sure,
idea from my side.
sure,
Can we design a program combinedly where we invite some students or some participants offline and start working for a week or so in IIT Kanpur or in REC Kannauj, whatever, wherever you find better. I am well conversant with that,
sure,
and we'll start from scratch.
sure.
Just like a person who is coming new. अब मैं तो कहूंगा कि मैं खुद सीखूंगा साथ में
नहीं,
बैठ
बिल्कुल बिल्कुल बिल्कुल।
इसमें
तो
कोई मैं तो सीखने के लिए हमेशा तैयार रहता हूँ। कोई ऐसी चीज मिल जाती है जो मुझे अच्छी लगती है, फैसिनेटिंग है नो डाउट ये एरिया, तो इसका हम प्रयोग अपने बच्चों के लिए बहुत अच्छे से कर सकते हैं, अपनी
बहुत बढ़िया,
फैकल्टी भी, क्योंकि सीखने के तरीके से ये बहुत अच्छी चीज है। तो
बिल्कुल
उसको जीरो से शुरू कर सकते हैं हम।
बिल्कुल
कंप्यूटर साइंस के कुछ टीचर्स, कुछ बच्चे अपने साथ रखते हैं, कुछ बाहर के बच्चे रख लेते हैं और
बिल्कुल।
बाहर के टीचर्स रख लेते हैं। वी विल मेक ए ग्रुप एंड विल स्टार्ट फ्रॉम स्क्रैच until the development of some new idea. So
ठीक है, ठीक है,
I hope that I'm sure that we can do something better.
ठीक है। तो मैं थोड़ा इसमें बैकग्राउंड दे देता हूँ और हिस्ट्री प्रोवाइड कर देता हूँ। तो टिपिकली वी कंडक्ट 1 month ऑफ सॉर्ट ऑफ ट्रेनिंग प्रायर
Yeah.
टू द वर्कशॉप। तो एक
Okay.
महीने का ट्रेनिंग होता है।
ठीक है।
उसमें अगर 100 बच्चे आते हैं तो उसमें से 50% के ऊपर छट जाते हैं। तो एक महीने हम लोग ट्रेनिंग देते हैं, वी टेल देम क्या क्या बैकग्राउंड जरूरी है।
बहुत अच्छा है।
उसके बाद उसमें अराउंड 30% जो बचते हैं उनके साथ 1 वीक का हम लोग ऑफलाइन सेशन करते हैं। और टिपिकली उस 1 वीक में टिपिकली लोग एक एक्सपेरिमेंट बना पाते हैं या 2 या 3 एक्सपेरिमेंट बना पाते हैं। तो बट ये एक महीने का प्रायर
ये प्रायर जो करेंगे
एक्लेमेटाइजेशन,
एक महीने का, ये ऑनलाइन करेंगे या ऑफलाइन करेंगे?
पहला एक महीना ऑनलाइन होता है, उसके बाद एक हफ्ता ऑफलाइन होता है। तो
एग्री।
दैट वे वी हैव इट इन 2 steps। तो
ठीक
जो
है
छट
सर,
जाए
तो
छट जाए।
हम लोग प्रोसीड करते हैं इस पर, इस आइडिया पर। इसके लिए आपको बहुत बहुत धन्यवाद। ये आइडिया पर हम लोग फॉर्मुलेट करेंगे, इसको रियल में लाएंगे। तो
बहुत
एक
बढ़िया
प्रोग्राम सर, डॉक्टर रवि, आई वुड लाइक टू रिक्वेस्ट यू प्लीज टू कोऑर्डिनेट विद सर, और
सर
एक प्रोग्राम स्टार्ट आउट कर लीजिए एक महीने का।
सर
हमारे बच्चे हैं वो भी साथ में रहेंगे, और जगह के बच्चों को भी हम बोलेंगे सब लोग आए। ऐसा कोई हमारे लिए नहीं, सारे बच्चे बच्चे ही होते हैं, ऑल द स्टूडेंट्स एंड हूएवर वांट टू लर्न, इवन द फैकल्टी मेंबर्स आल्सो। जो भी सीखना चाहे उसको एक महीने के लिए रोज सीखेंगे। और ये उससे एक फायदा होगा कि जो सीरियस लोग होंगे वो एक सॉर्ट आउट हो जाएंगे, जो वाकई सीखना चाहते होंगे, जो इसमें करियर बनाना चाहते होंगे, बिकॉज ये एक ऐसा एरिया है जिसमें कि स्टूडेंट्स अपने करियर भी बना सकते हैं, मुझे ऐसा लग रहा है। तो इस पर आगे काम करने के लिए आप सर से जरा टच में आ जाइए,
सर।
आगे काम करते हैं मिलके।
Sir, after the examination, I will offer to all the students for the opportunity.
तो सर
Surely,
से
after the examination,
एक
sure.
ट्रेनिंग,
बिल्कुल
एक
बिल्कुल
शेड्यूल निकाल करके पूरा एक फॉर्मुलेट करके फॉर्मल तरीके से बिल्कुल स्टार्ट करेंगे, तो एक
जी।
एक बच्चों के लिए भी और काफी हेल्पफुल रहेगा, मुझे लगता है
बिल्कुल
बहुत अच्छा
बिल्कुल
आइडिया है सर। और हमें बड़ी खुशी होगी आपके साथ काम करके सर।
बिल्कुल।
Sir,
आई थिंक हमको भी बहुत अच्छा लगेगा। और आई थिंक धनंजय इज द मेन की पर्सन यहाँ पे, तो धनंजय भी यहाँ पर है। क्योंकि धनंजय, इफ यू वांट टू स्विच ऑन योर वीडियो, ओके। तो इसेंशियली कई बार वीकेंड पे हम लोग ट्राई करते हैं या शाम के टाइम ट्राई करते हैं कि बच्चों को इनकन्वीनियंस ना हो उनके रेगुलर स्केड्यूल में। दिस इज एनी एडिशनल एक्टिविटी, तो उसमें भी हम लोग अकोमोडेट करने का ट्राई करते हैं।
नहीं सर,
और
मैं ये
स्पेशली
रोकना
या
चाहूंगा, ये
समर में।
एडिशनल एक्टिविटी नहीं है, ये उनके करियर से रिलेटेड एक्टिविटी है।
sir,
ये एडिशनल नहीं है, इसमें वो जो चीज सीखेंगे वो उनके लिए करियर में काम आएगी, उनका उनका
बिल्कुल
करियर बिल्डअप करेगी। ये देखिए, हर व्यक्ति बीटेक करता है, लेकिन बीटेक करने के साथ एक्स्ट्रा स्टार आपके पास में क्या है?
बिल्कुल
What additional you have in addition to the studying all those subjects who all people were studying? What the additional stars you have? That stars are these things.
हाँ। बट अगर मॉर्निंग में रखते तो कई बार वो क्लैश करेगा किसी और के
इवनिंग
स्टूडेंट
में
के
कर
किसी
सकते
और कॉलेज में।
हैं, हाँ नहीं, इवनिंग
दैट
कर
में
सकते
इंटरफेस तो इसलिए टिपिकली हम लोग ट्राई करते हैं कि इसको ऐसे टाइमिंग पे रखें कि कहीं क्लैश ना करे। बट
हैं।
यस, पॉइंट वेल टेकन, इट आई थिंक इट इज वेरी मच रिक्वायर्ड, उसको हम लोग डेफिनेटली परसू करते हैं। सो थैंक्स फॉर सपोर्ट शुक्ला जी, रियली
इसके
नाइस
लिए
नहीं
टू
नहीं,
सर
सी
प्लान,
बहुत
सर
अच्छा
इसके लिए
लगा।
प्लान किया,
सपोर्टिव है।
सर इसके लिए
रियली
और
प्लान
हम
किया
कभी
हुआ था,
चाहें कि
धनंजय सर और विनय सर से
आप
दोनों लोगों के साथ में।
सशरीर यहाँ आए, आप स्वयं आए तो बहुत अच्छा लगेगा। और एक
बिल्कुल
कुछ चीजें
बिल्कुल।
करके देखते हैं, या आप कहेंगे तो हमारे बच्चे आपके साथ आ जाएंगे, मैं भी आऊंगा, आपकी लैब में बैठ के देखूंगा, करूंगा काम, अच्छा लगेगा
यहाँ
मुझे।
पे थोड़ा मुझे लग रहा है अकोमोडेशन का थोड़ा दिक्कत हो सकता है, तो वी कैन प्लान एट आरईसी कन्नौज।
नो
वो प्लान
प्रॉब्लम।
करते हैं, तो एक बार जरा कभी ब्रेक मिलता है तो वी डेफिनेटली कैन
मैं
प्लान।
सर आपके रहने का पूरा इंतजाम करूंगा यहाँ।
हाँ नहीं, रहने का मतलब वो सेकेंडरी बात है, बट
नहीं
वहाँ पे थोड़ा सा आई थिंक
तो आने
अकोमोडेशन।
जाने का वो तो डेली आप आ भी आज आ भी सकते हैं, कानपुर इज नॉट वेरी फार फ्रॉम हियर, तो
सर,
कोई दिक्कत नहीं है।
सर वैसे कल धनंजय सर का भी यहाँ पर ऑफलाइन लेक्चर है, कल धनंजय सर की पूरी टीम आ रही है सर,
अच्छा,
यही
बढ़िया।
कैंपस में ही।
ओके
तो सर
ग्रेट,
उनको भी, हाँ वो भी कल स्टूडेंट्स भी रहेंगे, फैकल्टी मेंबर्स भी रहेंगे, तो कल उनका सर शेड्यूल है कल मॉर्निंग से ही।
बहुत बढ़िया।
बहुत अच्छा है,
बहुत बढ़िया।
बहुत
ओके सर, थैंक यू सर, थैंक यू।
थैंक यू, प्लेजर। आई थिंक बहुत अच्छा लगा सबके साथ, आई थिंक इंटरफेस करके, सो थैंक यू
बहुत
वेरी
अच्छा लगा, आपसे मिलके बहुत अच्छा लगा।
अरे
थैंक यू वेरी मच सर, थैंक
थैंक
यू।
यू।
अरे अरे मिल लीजिए सर, सर निकल गए, अरे निकल गए। ठीक है सर, तो थैंक यू सर।
सर निकल गए, तब तक आप देर कर दिए,
थैंक यू।
कोई बात नहीं, सर को बुलाएंगे, एक
ओके।
अच्छा सा एक ऑफलाइन सेशन करेंगे जिसमें की चीजें सीखें लोग, है
यस
ना। और बच्चों को ये बताइए कि ये उनके करियर के लिए भी अच्छा है, इट इज वेरी
यस।
गुड। ठीक है, चलिए
Thank you, participants. The feedback already is shared in the chat box and WhatsApp group. Thank you. So you can left this meeting. Thank you very much. Next session will start from tomorrow at 10:30 a.m. The link will be shared on in the WhatsApp as well as in the Zoom chat box also. Thank you.